Hello, this is Z Mathematics, and this is the first video of a series on Core Pure1 linear transformations as per request. So I'll make a few videos going over basically the whole chapter, and this first video today is basically just the intro to it, how matrices can be used to represent graphical transformations, and we'll be going over enlargements, invariant points, and just stuff to do with images and objects. So if we dive straight in, if we look over here, we've got a matrix 2002. Now this is our transformation matrix, and we'll see what happens in a second. We've got a set of coordinates over here, so we've got 0, 0, 0, 3, 3, 0 and 3, 3, which are the vertices of a square. Now, if we multiply it by this matrix 2002, when we multiply it by the point 0, 0, we end up with 0, 0 still. But when we multiply it by this coordinate 0, 3, we get 0, 6. When we multiply it by 3, 0, we get 6, 0. And when we multiply it by 3, 3, we get 6, 6. So this square over here is mapped to a bigger square over here when multiplied by this matrix. Now just some terminology. This original square that we started off with, that's called the object. And this thing that is mapped to is called the image. So the object is mapped to the image. So the object, which is this square, is mapped to this bigger square, and we can obviously see it's 2 times bigger. So this matrix over here, 2002, represents an enlargement of scale factor 2 about the origin. So this is what this matrix multiplication means graphically. Now a linear transformation transforms this general point xy to ax plus by cx plus dy. This transformation over here does not follow this, so it is not a linear transformation, because we're going from an x to x squared plus 2. Now x squared plus 2 is not in the form ax plus by, so it is not a linear transformation. And the same over here, this does not become cx plus dy. We're getting constants over here which isn't here at all. So therefore this transformation is not linear. Now this matrix over here, 2002, it is a linear transformation, it's a transformation matrix. But you may be thinking, oh, it's not in this form of ax plus by cx plus dy. Well, let's look what happens. If we multiply 2002 by a point xy, we end up with 2x, 2y. But that's not in the form ax plus by cx plus dy. But actually, if we look what happens, we get 2x plus 0y, 0x plus 2y. So actually it is in this form, but because there's zeros we can just cancel out, and we're just left with 2x, 2y. So this matrix over here is a linear transformation. Now invariant points and lines, we've met these before, like GCSE and probably A level I guess. If we have a transformation, so this transformation t, if it happens to the point xy, an invariant point will not change, it will stay the same. So it's mapped to xy, it doesn't change. If we look at this over here that we did, the invariant point is 0, 0, because it just stays the same before and after. Now an invariant line is where a line, if it undergoes a transformation, that line is still kept. The points lying on that line may swap around, but as long as they swap around to points that are on that line, the line can be classed as invariant. So if we have a pair of axes here and we have this line, now this line, if we pick out like 3 points on it, so if we pick out this point, and this point, if it undergoes a transformation, so we can draw the transformation here, if this point over here is mapped over here, if this point over here stays the same maybe, and if this point over here is mapped down here, the points are not invariant because they're mapped to different places, but if the same line is still created, they still lie on that same line, the line is invariant. Now we can represent this If we look at the equation of a straight line, we know it's y equals mx plus c. So our point xy can be written as x mx plus c. Because we're dealing with an invariant line, we don't need the exact coordinate, we need kind of the coordinate that's like on the line. So we have the mx plus c. Now, like I said, the points may transform, they may not be invariant. So we can represent this change of points by saying x is mapped to x dash. Here the invariant point, x was just mapped to x and y was just mapped to y. But here x is going to be mapped to x dash because it could be a different point. But this mx plus c is mapped to mx dash plus c. Because if the straight line is invariant, the gradient and y-intercept are going to be the same. It's just going to be the points that change. So there's an x dash there, but the straight line is still the same. So it still has the same gradient and y-intercept. We'll do some exam questions on this to get a bit more used to this and see what we can use it in. Now, stretches. Stretches are, I guess, similar to enlargements, but this enlargement is basically like a special type of stretch. So if we just do this, if we draw a set of axes, now, if we have our basis vectors 1, 0 and 0, 1, they create our identity matrix 1, 0, 0, 1. Now, if it undergoes a transformation, and this transformation is going to be a stretch. So this 1, 0 over here will be stretched out, let's say over here to k0. Well, actually, let's say a0. And this point 0, 1 is going to be stretched up here to 0b. We're just generalizing it for like a general stretch. The new matrix is going to be a0, 0b. Now, what has happened? Our, I guess, x coordinate of 1, 0 has been stretched to a0. So this a0 is specific parallel to the x-axis because it's like basically on the x-axis. And it's the same for the y. The 0, 1 got mapped to 0b. And that specific is like parallel to the y-axis. So this matrix over here, a0, 0b, is a stretch, and parallel to the x-axis, the scale factor is a, and parallel to the y-axis, the scale factor is b. Now there's a special case. If a equals b, like over here, this is in the form a0, 0b. So a equals b over here. That's like a general enlargement like we saw over here. So I guess it's parallel to both the x and y axis in the same magnitude. Now for this stretch, a0, 0b, when it's parallel to the x axis, when we have the stretch, if it was just like a0, only this axis will have like a change of points. This could stay as 0b. So this could be invariant. So the points on the y-axis are invariant to the stretch parallel to the x-axis. And the y-axis is the line x equals 0. So for the a0 part, the stretch parallel only to the x-axis, the y-axis is invariant, or the line x equals 0 is invariant. And it's the same for the y-axis. On the y-axis, only points on the y-axis will be like stretching. That stays invariant, so the line y equals 0, which is the x-axis, is invariant. Now let's do an exam question that like covers what we've just done. So part A. So A is the matrix over here. A and B are non-zero constants. Given that matrix A is self-inverse, right? So matrix A is self-inverse. The chapter before this was matrices, so you should know about the inverse of a matrix. So if it's self-inverse, the inverse of A is literally, so it's 2A minus 4AB. Determine the value of B and the possible values for A. Now, because we've been told this piece of information, we know what the inverse matrix of A is, and we've been given A in the question. So what links a matrix and its inverse? Well, if we multiply a matrix and its inverse matrix together, we get the identity matrix. So a, which is 2a minus 4 ab multiplied by itself, that is equal to 1001. Now, using our matrix multiplication, we're going to multiply the 2 and 2 and the a and a minus 4. So what we get is 4 added to a times a is a squared minus 4a, and that is equal to the 1 over here. So that's 1. So we get a quadratic. If we subtract 1 from both sides, we get a squared minus 4a plus 4 minus 1, which is 3, equals 0. Now this factorizes to a minus 1, a minus 3 equals 0. So a is equal to 1, or a is equal to 3. So I guess we found our possible values for a now. Now we have to find the value of b. So the part that will have a b in it is when we multiply this, and that will give us the top right number 0. So what we get is 2a from here plus ab is equal to 0. So 2a plus ab is equal to 0. Now because we had two values of a, let's try it for both. So when a is equal to 1, 2a plus ab is 2 lots of 1 plus 1 lots of b is equal to 0. So 2 plus b equals 0, b equals minus 2. And when a is equal to 3, we get 2 lots of 3 plus 3b is equal to 0, 6 plus 3b is equal to 0, and we still get b equals minus 2. So a is equal to 1, 3, and b is equal to 2. That's our final answer. Now part B. The matrix A represents a linear transformation M, using the smaller value of A from part A. So the smaller value of A is 1, so we're going to be using A equals 1. Show that the invariant points of the linear transformation M form a line, stating the equation of this line. So we have to show that the invariant points. Now the invariant points on this slide, xy is mapped to xy. So the matrix A represents a linear transformation. So first let's write A using our value of A equals 1. So we've got 2. A minus 4 is 1 minus 4, which is minus 3. A is 1, and then B is minus 2. So if we multiply this by xy, because it's invariant points, we'll get xy. So now we do a matrix multiplication. So what we're going to get is 2x plus y is equal to x. So 2x plus y is equal to x. Subtract x from both sides, we get x plus y is equal to 0. And that's the equation of a straight line, or y equals minus x. But let's do the matrix multiplication on the other side. So minus 3x minus 2y is equal to y. So minus 3x minus 2y is equal to y. Subtract y from both sides, minus 3x minus 3y is equal to 0. Well, hey, that's just the same as x plus y is equal to 0. So our invariant line is, so the invariant line is x plus y is equal to 0. Now we've got the mark scheme over here, so that was for part A. So A is 1 and A is 3 and B is minus 2, so we got that correct. And then part B, x plus y is equal to 0, so we got that all correct.